those who don't know me, my name is Anthony Peake. I am self-evidently English and an English writer. I've written somewhere in the region of 13 books now, and some of you may know my work, and some of you, this will be the first time you'll be introduced to my work. Over the next few days, I'll be doing a series of lectures, workshops, intensives, and panels. They're working me very hard this year, but it's really good. I'm really honored that they wish me to do this. Now, what I'm going to attempt to do now is almost the impossible. I am not a physicist, but over the last probably 2 or 3 decades, I've invested a considerable amount of time trying to understand quantum mechanics in a way that the layperson can understand, because quantum mechanics is the basis of everything. And therefore, in terms of Paul's presentation just before, it's the idea of exactly what is reality and what do we mean when we talk about reality. Because it's only when we can understand what reality is, we can start looking at this phenomenon. And indeed, the other phenomenon I write about, from out-of-body experiences to near-death experiences to lucid dreaming, all these areas are all areas that I discuss in great detail in my books. So without further ado, let's see if it works. I've worked on this presentation to try and get it as clear as I possibly can. So let's go through it systematically and hope that the technology works. Okay. Everything we see around us, we think is physical matter. We think it's solid and we think it's real. But the problem is when you start looking at physical matter, you'll find that it's not. In fact, everything that we perceive is made up of just a handful of subatomic particles. Then on the first side, we have things called leptons, which are effectively physical objects, physical bits of matter that we have. And these are effectively an electron neutrino, a muon neutrino, a tau, and a tau neutrino. But effectively, for all intents and purposes, in terms of the reality we perceive, all we should be interested in is electrons. And electrons are effectively very tiny little charges of negative electricity that spins round the atom. Very, very tiny. And then everything else that's physically made up within the atom is made up of things called, well, I call them quarks. A lot of people pronounce them as quarks. The reason they're called quarks is because that is what the original person that came up with the idea called them. And the word quark actually comes from the James Joyce novel, Finnegan's Wake. And they used it for that reason. Now, in terms of quarks, there are 6 of them. And each of the quarks just come together to create other subatomic particles, such as the up has an electric charge and a plus and 2/3 and contains two neutrons. A neutron contains 2 up quarks, for instance. So all of this, that is the whole building block of everything you perceive around you, literally everything, including you, including your consciousness. Everything is made up of just these handful of particles. Now that's of profound importance because we've got to understand exactly what we mean when we talk about solid reality. For instance, in terms of the only reason that the floor below me, I'm not falling through it, is because of something called electrostatic repulsion, which effectively means that the edge of every atom in this table and this floor, not just the atoms, but the molecules themselves, the edge of each atom is electrically charged, as are the atoms in my feet. So the reason I hover over them is that the charges in my feet, the electrons at the edge of the atoms in my feet, are negatively charged, as is the edges of the atoms in the floor below my feet. And as you know, what happens if you have like charges? They repulse. And that's effectively what's going on. So you never actually ever touch anything. So when you say in life that you touch things, you don't. Your whole life, you never touch anything. You hover above it. And that's of profound importance, again, when people say that if I touch something, it's real. Then you have to take into account the atoms themselves. An atom is 99.99999999996 empty space. And what is physical in there is the quarks, and the electrons. Now, quarks and electrons are called point particles. And a point particle has no extension in space. However much you zoom into a point particle, you only ever see a point. Now, let's start thinking about this for a minute. So that means all the reality we see around us is made up of tiny, indivisible, tiny points. And all these points come together to create what we call physical reality. Now, let's just look at another element. So we've discussed matter, and now I want to talk about light. So let's use a bit of matter of, this is an even better one actually as an analogy in terms of this. So how much matter is in each atom? So many of you will have a gold ring on your finger. Feels fairly solid. If you touch it now, it feels fairly solid, doesn't it? But a gold atom, the distance in terms, if we were talking about distance in terms of different sizes, the central nucleus of a gold atom, if it was the size of a millimeter, the actual electrons that are whirling around the outside would be 3.3 miles away. That's how much empty space is inside each individual atom. So then we'll touch on to light. Light is the things that you see. This light, as an example, light is effectively an element of what's called electromagnetic energy. And the electromagnetic spectrum is a spectrum of the different wavelengths of light. Effectively, they go from radio waves, which are very big, to gamma rays, which are really small. Now, we believe that everything that is physically out there is given to us by vision, isn't it? So we see things, so we believe that they are real and they are tangible. Now, I came up with an analogy a few years ago. Imagine that the electromagnetic spectrum as a line is the Mississippi River. The Mississippi River, as you know, starts in a tiny lake up in Minnesota, and it winds down through the center of the United States, and it gets down and it comes out in the Gulf of Mexico. The world we believe to be the visual world, that is visible light, would be, using that analogy, 1.5 inches, about 8 miles south of Hannibal, Missouri. That is what we believe is the visual world. So we believe that everything we see is real in some way. But it's not. I mean, I'm already going off piste in terms of doing the talk, but I think it's important here. For instance, the color red does not exist anywhere. None of the colors you see exist anywhere. They are literally just vibration states of electromagnetic spectrum that our brain interprets as being red. But red is nowhere. You look at a red rose. There is no red in the rose. There's no red in the waves coming to your eyes. There's no red in your eye. Red is nowhere. And when you start to realize this, you start to realize that everything we perceive is being interpreted by the brain. For example, you're now looking out at me talking. What is actually taking place is that photons of light are bouncing off me, and they are entering your eye, and they go into your eye through your pupil, and they hit the back of the eye, a place called the retina. The retina then converts that into an electrical signal. So no longer is it light, it's an electrical signal, which is then transferred to the darkest part of your brain, right at the back here, visual cortex, where those images are then recreated. Now, the image on the retina is about 1.5 inches high, and it's inverted, and it's bent. And that's the source of the information. Now look around you and realize that what you are seeing now is being processed from that very small piece of information. And the brain changes that bit of information to this sensory surrounding you visual world. It's a magical trick. And in my books, I even talk about the contrast of exactly what's doing the interpreting in the brain. Where are you in your brain? There's something perceiving this information. And in my other talks, I'll talk about that in greater detail. But now let's look at this. Light, we tend to think as being tiny little bits, again, of matter called photons. Well, it's not even matter, but just bits, technically, of information. So we believe that light is a particle. And the reason we know this is because if you take photographs taken in dimmer and dimmer light, they look grainier. And then as you get more and more of the photons hitting the screen or hitting the image at the back, you get an image. But when we detect very weak light, we find it's made up of these particles and we call them photons. But what exactly are photons in reality? And they are very, very mysterious. So the things that make up light themselves are strange, and stranger than you can possibly ever imagine. So they believe, is light a wave? Because we've just been discussing them being a particle. But if we start looking at light properly, we find that it has a wave-like property. It seems to flow around things. But it's a particle as well. How can this possibly be? It diffracts around a penny. If you're watching rain fall, you'll see rainbows and things, again, giving you the idea that it's a wave. The problem is, though, that a wave is like a wave in water. You drop something in water and the waves come out from the area. But what exactly is waving when we're talking about light? Because the difficulty is, for instance, there's 96 billion miles between the Earth and the Sun. So how do light waves get from the Sun to the Earth when it's a vacuum? What exactly is waving? Is space waving? But space is empty. So the only logical argument is they must be tiny points or photons. But they show both categories. It can be a wave and a particle. And the question is, what makes it the decision to become a wave or a particle? And they do a certain degree of tests. And it's called the twin slit experiment or the double slit experiment. And put in general terms, it's literally, you just fire waves or particles through two slits. And they found some incredibly curious things take place when you do this. So if it was a particle and you fire a single particle through, what would happen is the particle would whiz like a tiny little bullet. And it would go through either one of the two slits, because of course a bullet can only go through one or the other. It can't go through both, can it? It has to go through one or the other. So in this particle, it would go through one slit, and you'd end up with evidence of light hitting a screen at the back. If it's a wave, the light source waves out like a water wave. And what happens is they spread out and they go through both slits, causing what's called interference patterns. Because when the wave hits that, it gets broken into another wave. You can visualize it. The waves go through and they hit, and then they interfere and cause an interference pattern. And you end up with light and dark bands. So they're two very different phenomena, aren't they? They're completely different. But light shows both, given certain circumstances. So what scientists decided to do is to find out what was really happening here. So what they did was they decided that they would send a line of particles. A particle emitter is something that just fires single photons of light. And they fired them towards a single slit. And of course, what happens is the particles come through, single particles, and like kicking a load of footballs through a doorway, all that will happen is at the other end of the door, you'll get just a collection of footballs in one location. And that causes what's called a diffraction pattern, which you see there. But what happens if you use the two slits that I was saying before? So let's go back to this again. So the particles come along and they go through either one slit or the other. And in doing so, they create another diffraction pattern. But if you send them through the two slits, what will happen is you'll get this kind of collection of these will all join together and cause larger numbers of particles. And you get a second diffraction pattern. So what the scientists decided they would do, I'm not going to go through with this, but that's, again, how with water. So you drop a drop of water and the waves come out. And as we said before, they go through and they cause that kind of pattern. Because it's a crowd wave, a phenomenon like waves in water. But they decided to do a clever experiment. They decided to just fire one particle at a time. So you have a gun, and it's firing one particle. So logically, the particle can only go through one slit or the other. So it can go in that direction and cause a pattern like that. But how can a diffraction pattern, which involves the interference, occur when only one particle goes through one of the two slits? In other words, how can it interfere with itself? It's only going through one at a time. So an interference pattern suggests there's interference going on, but there's only one particle going through at a time. So what the scientists decided to do was effectively, and I'll go through this because it's just giving you the idea of how the particles come together, is to put a measuring device on one or other of the slits to see which slit the particle goes through. Now, this is where it gets freaky. What they found is that if you put a measuring device on there, the wave turns into a particle, as if the particles know they're being watched, as if the particles are aware in some way that there is an observer watching them. Now, this is curious. Now, this suggests that particles seem to have a direct relationship with the act of measurement or the act of observation. And every time they do this experiment, twin slit experiment, the same thing happens. If they put a measuring device on, it's a particle, and if they don't, it's a wave. We can never see the waves going through. Now, the implications of this are astonishing. It's just explaining how this happens. Because this is astonishing. Because what they then decided to look at was saying, well, if it does it with light waves as tiny particles, what if we fired electrons? Now, electrons are tiny bits of matter. They're not a photon, because let's make a point about a photon just for a second, the light you're seeing at the moment. A photon, as I said, is also a point particle, so it has no extension in space. But what is also interesting about photons is they can only ever travel at the speed of light. Now think about that for a second. They can never slow down. They can't accelerate to the speed of light. They can only ever travel at the speed of light. So when you put a torch on, wow, that was good. How did I do that? So when you put a torch on, that was weird, wasn't it? Did somebody just switch the lights on? Well, I'll try it again. It didn't work. So if you then, I've actually lost my train of thought now as well. So the particles move. They can only travel at the speed of light. Now, there's something we know that's quite interesting about the speed of light. Now, that's the point I was going to say. You switch a torch on, the particles will come out of the torch, but they can't accelerate. You know, when you're in a car, you start at 0 speed and you accelerate to 60 miles an hour. With light, there's no acceleration to the 60 miles an hour. It just is at the speed of light straight away. There's no acceleration. They're just at the speed of light. But on top of that, some of you who know your physics will know that at the speed of light, something very curious happens. Time stops. There is no time when you travel at the speed of light. So the viewpoint of a photon is there's no time. So the photons that are hitting your eyes now are not leaving from their point of view, they arrive at your eye the moment they leave my body when they're bouncing off. And the same goes for every single photon of light. So when you're looking at a quasar, which is billions of light years away, as far as that photon is concerned, it's the same instant that it left the quasar. And it left the quasar billions of years ago. So suddenly the idea of how we see things and how physical reality is starts to break down. And this is all known science. This is not strange, weird stuff. This is the real deal. But when they decided to fire the electrons, the little point particles that are physical, they found the same thing happened. You've got the twin slit experiment, and again, they discovered that in certain circumstances, little points of matter are also waves, and they're also particles. And they are also affected by the act of measurement or the act of observation. So this means that physical matter not only is 99.99, as I said before, empty space, but it needs somebody measuring it or observing it to bring it into reality. And Max Born, a physicist in the 1930s, came to the conclusion that everything has a wave function. Everything is a wave. Everything that is physical is a wave, a non-physical wave. Now, when we use the term wave in physics, we're not talking about like a wave in water. What we are talking about is a mathematical wave, a mathematical chance of finding a particle in a particular location or another. It's mathematical. It's digital. So suddenly, again, the idea of what is physical matter is suddenly starting to disappear, if you're all following me, and I hope you are. But it starts to disappear. As soon as you start to think about it, it starts to disappear. But it gets stranger again. Because, of course, electrons are still very, very tiny. So therefore, that they have these strange qualities is odd, but it's not that strange. They're like photons. However, and this is where it gets very strange. They've been doing the twin slit experiment or the double slit experiment with molecules. Now, you know from your childhood and your school physics and chemistry that a molecule is a collection of atoms that are put together in a particular way in a compound to create a new substance. Suddenly they're getting bigger now. And the thing is, they have discovered that large, very, very large molecules do the same thing. For instance, Buckminster fullerene or buckyballs. They have 70 atoms in the structure. You fire them through the twin slit experiment, they do exactly the same thing. If they're not observed, they're a wave, and the moment they are observed, they collapse into a particle. Buckyballs. They thought it was something to do with the shape of a buckyball. Buckminster, it's shaped like a ball, hence the name buckyball. They're good, aren't they? How they do that. But they found that something called fullerene, which is a very different structure, that does the same. And it has 1,632 atoms in it. That's big. And then they thought, okay, maybe it's the shape of them. And then they find this stuff that I can never pronounce properly. It's tetraphenylporphyrin. And that's a biomolecule that shows the wave particle function. Biomolecule. Biomolecules are the things that create life. So suddenly the things that create life itself are showing these strange relationships with the act of observation. So suddenly the universe is getting very, very peculiar and very, very strange. Suddenly what we think is solidly real suddenly isn't. And the question is, and most scientists will argue this, is when we talk about the act of observation, do we mean the act of measurement? Do we mean that it's the measuring device that is the thing that's causing the wave, or what's known as the wave function, to collapse? But in the final analysis, a microscope, it only functions when somebody looks through it, doesn't it? You're only making these measurements when somebody makes the measurement. Effectively, a ruler doesn't measure anything until somebody holds the ruler and says, that's 6 inches or that's 12 inches. So we're coming back to the idea of the observer or the brain collapsing the wave function in one way or another. So suddenly there seems to be a relationship between what we see and what we perceive. So as I say, reality is brought about by an act of observation. No observer, no reality. But who's an observer? I'd always loved this cartoon. I don't know if you can see it properly, but it's the idea of this guy explaining that what I've been just telling you now is called the Copenhagen interpretation. And it says, of course, application of the Copenhagen interpretation of quantum theory to macroscopic objects is clearly ridiculous, because it would imply that everyday things exist only as the superposition of all possible states until we actually observe them. And if you can see what he's doing, he's talking, and there's this superposition state, which I'll explain in a second. And he turns around, and there's a person there. And he turns away again, and she's turned back into a superposition state. Now, again, some scientists have actually argued that reality is rendered by you looking at it. So in which case, for instance, the back of my head doesn't exist for me, and I don't need to render it. It's you guys that's rendering that by observing what's behind me. So the idea that atoms and molecules are only coming to physical existence, called the Copenhagen interpretation. And this is the theory believed by most quantum physicists. And this is important to realize this. This is the standard model. This is what most quantum physicists believe genuinely happens. This is what reality is believed to be. But Albert Einstein refused to believe this. He said, this is ridiculous. I can't believe that the moon doesn't, the quotation, he said, I cannot believe that the moon does not exist if I'm not looking at it. And he argued this, and over many years, he put a lot of thought experiments together to argue with the main guy who was behind the Copenhagen interpretation, which was a guy called Niels Bohr. And every time that Einstein came up with a model, Niels Bohr would come along and knock it down. And one of the lines was, Einstein said, I cannot believe that God plays dice. You know, the idea of statistics. And Niels Bohr's response to that was, Einstein, don't tell God what to do. So clearly that's how the route went. So Einstein and his associate Erwin Schrödinger came up with a thought experiment about the idea of subatomic particles coming into existence by somebody observing them. And they said, this is ridiculous. And we'll show it's ridiculous. Imagine a circumstance where you place a cat into a sealed box. And so at 1 o'clock, you put the cat in the sealed box and you lock the box. Now, inside the box is a phial full of poison. And near to the poison is a hammer that will swing over and smash the box and release the poison. There's a detecting device up here, and it's programmed to the fact that if a particular subatomic particle changes its state or decays or whatever during an hour period, if during that period it decays, the signal will be sent to this, which will then come down here and tell this to smash the phial and kill the cat. But the problem is, during the hour, if we argue the cat is not an observer, the cat and the poison and everything else and the subatomic particles aren't observed. And if they're not being observed, technically, according to the Copenhagen interpretation, they're only a statistical wave. They don't exist. So the argument is that for an hour, and the scientists do not know whether the poison has been released or not, the cat is both alive and dead at the same time. Because it has to be, because nobody's observed it. So therefore, it must be an alive and dead. And this is the Schrödinger's cat experiment. So at 13:15, suddenly, a subatomic particle gives off, bang, the cat is killed. So there's a 50-50 chance that the cat might die in that period. Now, the problem is, as we said, until the box is open, the cat is both alive and dead, as predicted by Copenhagen. So this has a very peculiar thing then, if this is the case. It means that can a cat be alive and dead at the same time? And in 1957, a young scientist by the name of Hugh Everett III, in his PhD thesis, came up with a supposed answer to this. This is the other alternative. So the first alternative is that reality is created by the act of observation. Alternative is even more interesting. The alternative is that after observation, when the box is opened, one scientist sees a live cat and one scientist sees a dead cat. At that point, the scientist splits into two. And there are two scientists, one who sees a dead cat and one that sees a live cat. This is called the Everett's many worlds interpretation of quantum mechanics. And this is how they come up to the idea of multiple universes. Because the argument is that the universe has been splitting at every subatomic incident since the first moments, the first nanoseconds of the Big Bang. So literally there are trillions of universes out there. And every second, they double and double and double and double. Now, an extrapolation of that is then very interesting because it can explain one of the greatest mysteries of science. And it's the mystery of what is known as the cosmic anthropic principle. And the cosmic anthropic principle is the idea that when scientists started looking at the time after the Big Bang, they noticed something very strange. For instance, in the first millisecond of the Big Bang, there was a slight preponderance of matter rather than antimatter. And if they'd been equal, they would have destroyed each other. So the universe wouldn't even have started at the first microseconds of its existence. And they found a whole series of really interesting coincidental events to bring about the fact that me and everybody in this room evolves. We evolved from our ancestors, and we evolved in such a way to become observers of reality. Now, there are little things like, it's fascinating, and I find this always extraordinary. Water is the only liquid that freezes from the top downwards. Every other liquid freezes from the bottom upwards. If water did it the other way around, life wouldn't have evolved on Earth. But there are other things, there's balances, there's so many of these things that happened coincidentally to allow us to evolve. Now imagine there was only ever one universe. If there's only ever been one universe, this universe got it right for the evolution of consciousness at one attempt. If there's only ever been one universe. So the alternative is there are trillions and trillions and countless universes. And most of them, life never evolved. And we just happen to be in the Goldilocks universe that life evolved in, which is true, isn't it? You know, it's logical to conclude that you're going to be in the universe where life evolved. But if there was only ever one universe, that wouldn't work. So then we get some very, very strange ideas about the nature of reality. Because you can actually extrapolate, if you argue the twin slit experiments on Schrodinger's cat as being the evidence of reality and not the many worlds interpretation, you can prove that each one of you in this room is immortal using science. A guy called Professor Max Tegmark, who is a Swedish guy, I think he's at the University of Princeton now. And he did a thought experiment applying the ideas of Schrodinger's cat. And he argued, imagine a scenario that instead of a cat in a box, there's a scientist in there. And the scientist is inside, and the scientist is locked in the box. Now, as I say here, a scientist is hypnotized, that he's absolutely no observational abilities. He's locked in a sealed room in the same way, and the same thing happens, that he may die or he may not, depending on when the particle happens or not. But it effectively means that there's a human being inside the box who may or may not be alive. And the argument is, and this is very intriguing, that after observation, there is a dead scientist and a live scientist taking place. So which scientist is the one that survives? Tegmark argues that if Copenhagen is correct, we all survive. And the reason we survive is we are the observers of our own universes. That our universe comes into existence because effectively we are observing it. And one of the points I'd like to make now, and it's something I make in talks quite regularly, every single person in this room, there's one thing that you've observed in your life. You've survived, haven't you? You know other people that have died, but you're still here. You survive and continue to observe. And if anybody's interested then in my model, I argue that I can prove scientifically that we never die and that we continue and we survive. I call it cheating the ferryman. And I'm applying a lot of this physics to the fact of potential human immortality. And what is then weirder is that John Wheeler, who was a very famous quantum physicist, argue that you can prove that not only does your act of observation bring in this universe into existence, but it also brings in the universe in the past into existence. Now, bear with me on this one. What I'm going to argue and what I'm going to apply is Wheeler's interpretation of the twin slit experiment. I hope I've got it here. Yeah, there you go. What Wheeler said was, imagine that you could create the light, take the light coming from a quasar. Now, quasars, quasar-stellar objects, are huge sources of energy in the universe, but they only existed for the first few billion years of the universe. So when we see quasars now, we're seeing the light as it was billions of years ago. They're no longer there. They no longer exist. But their light is still getting to us. And he said, imagine doing the twin slit experiment where the light came from the quasar. And what happens is there's something called gravitational lensing. When light goes round a mass object, like a galaxy, it gets bent. So what will happen is the light from the star, the quasar here, will bend round a galaxy. So what you'll end up with is seeing something called an Einstein cross, where you'll see the light as if there's a cross and there's 4 stars, but in fact there's only one, but it's the same light source. And he said, imagine if you could place out in space the same kind of idea of the twin slit experiment, and the light from those 2 sources goes through one slit or the other. Wheeler argued that at the act of observation of the person seeing the experiment brings into existence the quasar that hasn't existed for billions of years. Now that's extraordinary. Now the reason this makes sense is because there's one thing I haven't brought into in the whole argument so far: time. Time is the most peculiar thing you can imagine. St. Augustine, when he was asked whether he understood what time was, said, I think I understand it if I don't think about it. But the moment I start thinking about time, I realize I don't really know what it is at all. And this is profoundly important, because rather, like I said, that you cannot identify the color red to somebody else because you can't describe red only by saying, well, it's a little bit like orange. But you can't objectively prove to anybody else that the red you see is the red that somebody else is seeing, because you can't. The same goes for time. If you turn around and say, oh, I just perceived 10 minutes go past. But is your 10 minutes the same as somebody else's 10 minutes? Because you only can ever measure time by looking at a watch, which of course isn't actually measuring time, it's measuring geometry because it's moving around. So time is only ever measured by itself. You can have a minute of a minute or an hour of an hour, but you can never, ever turn around and measure that objectively. I mean, for instance, have any of you ever been involved in a car crash or been given bad news where time suddenly goes and you feel it traveling slowly and slower? How can that be? Because is your time different to somebody else's? I know people that have been involved in car crashes where they've had sufficient time to negotiate their way round the car crash. The reason is because their processing of time slows down to such an extent they can escape a car crash. So what is taking place there? So suddenly when we're talking about time and billions of years ago, we don't really know what that means. Time effectively is, as the scientists will say, is something called entropy. It's the idea of something going from order to disorder. As the universe expands, things get more disordered. But that's not to do with the observer as such. Somebody having fun over there. People always do that, don't they? They always phone you at the wrong moment. So if you then bring Tegmark's idea, that means that the universe needs an observer to come into existence, doesn't it? It means if these quasars come into existence by the act of observation, suddenly there's a relationship between what we are as observers and what is out there. So suddenly the role of consciousness becomes profoundly important. But it then gets stranger, because there's something else that's been discovered in recent years that is beyond comprehension, that the vast majority of people do not know about. It's called superposition or entanglement. And what they found is, well, we'll go back to Einstein. Einstein had profound problems with the Copenhagen interpretation. And one of the things he suggested was a thought experiment in 1937, which was called the Einstein-Podolsky-Rosen experiment. And in this, he argued that if you sent two subatomic particles off in different directions, and nobody was observing them, and you did something with one particle, what would happen to the other one if you entangled them? Because what happens is if you put two particles into the same quantum state, and I can't go into detail what a quantum state is, but they're similar. You put them into different directions in space and in time. Effectively, if you do something with one, it affects the other one. Now, what happened was they reproduced this experiment in 1980. The guys called Alain Aspect and Dalibard in Paris. And what they did was they took two particles, entangled them, spread them in different locations. And they found if they did something to one particle, the other one reacted instantaneously. Instantaneously. In other words, there was no time lapse for the message to go. It was faster than the speed of light. And they came to this incredible conclusion that once particles they have the same state, they can communicate with each other instantaneously when they're close together. Now, let's think about this for a second. 13.4 billion years ago, there was the Big Bang. Before the Big Bang, every single particle in this universe, every single particle in your body was part of a point state. The whole universe was in a point state, which means that every single particle in this universe is entangled anyway, which means that particles can communicate instantaneously. Now, again, you might turn around and say, okay, but what's the practical solutions for that? Well, there's a guy called Anton Zeilinger at the University of Vienna, who's been doing a series of experiments where they've been entangling particles and placing them at different distances. And they're getting hundreds of miles difference, and these particles still communicate instantaneously. It seems that at a deeper level of reality, everything is related. So let's recap what I'm saying here now. So suddenly physical reality that you believe is physical reality is 99.99 whatever empty space. What those particles are actually made of is nothing. They are point particles. That everything you think you are seeing that has been created by your brain is literally creating an internal model of external reality. That particles can be entangled. That cats can be alive and dead at the same time. And all these things are modern science. So where are we now? Well, we'll have the Niels Bohr idea, the Copenhagen interpretation, that the universe needs an act of observation to come into existence. That's option one. Option two, Hugh Everett, the many worlds interpretation, that the universe splits at the every act of observation. You then have a guy called David Bohm, and this gets very interesting because David Bohm was an American physicist who fell foul of the McCarthy witch hunts in the 1950s. And he ended up moving down, I think, to Argentina and then ended up in London. And he said, neither of these things are right. He said, there's another better alternative, that a deeper level of reality, there's a different reality, a deeper level. And it's interesting what he argued. And again, follow me on this. The smallest possible size we can imagine scientifically is called the Planck scale or the Planck square, which is really tiny. But the smallest thing we can actually observe using our machines in terms of size is something like 20 or 30 times bigger than that. So in terms of size, there's this huge area of reality that we cannot measure and don't even know what's taking place there. And he argued that really what the universe is a hollow movement. It's like a hologram. And that the universe is made up of information, data. And he argued that everything we perceive is actually is something coming out of this information field. And he called it the implicate and explicate orders. And the explicate order is what we perceive. And everything we perceive is being generated literally by numbers, by mathematics. So the universe is mathematical in its structure. There is no physical reality. It is just maths, which means that the universe effectively is like a bloody big hologram. And then Carl Pribram, who was at Georgetown University, came up with a similar conclusion about consciousness. He argued that consciousness works holographically. So if he's right, that means a hologram is being processed by a hologram. So suddenly we've got this sort of thing creating itself almost. Now, the reason they believe that consciousness is a hologram is because of one of the greatest mysteries of consciousness, which is something I'll be talking about in my other talks. And it's this. It's called the binding problem. All of you at the moment are having a feeling of simultaneity. You feel that, say, for instance, you see a red ball bouncing down a street. You see a red ball moving down, but different parts of the brain are processing what you're seeing in different parts. So the red is being processed in your visual cortex, the movement is being processed in another part of the brain, and everything else you're seeing around is being processed in different parts of the brain. Now, communication in the brain through neurons it's not like the speed of light. It's much slower. But we get a feeling that everything is happening now. They don't understand how the brain does that. And if ever you want to embarrass somebody who's a materialist reductionist, just say the binding problem. How do you explain that? Because they can't. So it means that the brain must be functioning in a completely different way to the way we think it ordinarily functions. And again, one of the things that I've recently found from my friends who are doing leading edge research in brain analysis and working with dimethyltryptamine and working with psilocybin and other mind-altering substances is something extraordinary. And it's something that only happened comparatively recently. They actually, at the University of Sussex in the UK, they rigged people up and gave them magic mushrooms, psilocybin. And they had an fMRI scanner of the brain, so they knew exactly what the brain was doing exactly every second. They gave them psilocybin, and they were expecting to discover that the brain started to link. In other words, to create the hallucinations, that bits of the brain would start lighting up that didn't normally light up. That's not what they found. In fact, the opposite happened. Parts of the brain switched off. The brain wasn't it was literally, the psilocybin was stopping the brain cutting out information. In other words, when we think that our brain is giving us all the information that's around us, it's doing the opposite. It's taking information out, and it's taking information out for one very good reason. Because if you were sitting there now and all the information your brain is receiving from how your fingers are hurting, you've got an itch somewhere, you're hearing voices outside, you have to attend to what's in front of you, like listening to me, hopefully. So the issue there is that the brain takes things out. Now, if the brain takes things out, what is it taking out usually when we're in everyday consciousness? And I have a concept in my books that I call the Huxleyan spectrum. And what I argue is, depending upon where you are on the Huxleyan spectrum is how you perceive reality. Now, I would argue, for instance, is there anybody in the room who's a classical migrainer? Okay. Do you get scotomas? Do you get breakdown of your visual field kind of thing? That's because the brain is functioning in a different way. I'm a classical migrainer. I get profound déjà vu sensations when I actually have that. Then if you move along from there and you get to the higher levels of migraine, you move over into something called temporal lobe epilepsy. And people who have temporal lobe epileptics perceive the world in quite a different way when they're actually in the aura state. They see things we don't normally see. Then you take it further and you get schizophrenia, where the doors of perception are wide open. So what it means is the brain is acting as an attenuator, but these unusual neurological circumstances seem to open the doors and make it wider. So coming back full circle, So when we were saying about how little of reality do we actually perceive, suddenly it's all brain generated. And when your brains function in certain ways is how broad this is going to be. I mean, I'll give an example of this. If anybody goes onto my YouTube site, my YouTube channel, there's a young lady I interviewed live on my show about 2 years ago, called Rebecca Sharrock, and she's autistic, and she's only one of 8 human beings, I think, in history that has what's called superior autobiographical memory. She remembers absolutely everything that has ever happened to her, including her dreams, including being in the womb. And I tested her live. I didn't tell her I was going to do this. My assistant's daughter loves Harry Potter, as does Rebecca. So I said to Rebecca, so you remember everything in your life? She said, yes. And I turned around to my assistant, Sarah, and I said, okay, Sarah, can you take out all the books that your daughter has, the Harry Potter books? Can you pick one at random? Which she did. And then I said, can you pick a page at random from that book? And then can you open that page and can you pick a paragraph at random? And can you read what it says? And I told Rebecca, can you tell me what comes next? She got 3 or 4 words in, and Rebecca gave the whole paragraph, word for word. Now that technically is impossible, unless the human brain is far more extensive than we can possibly believe, but we are ordinarily denied it because the brain acts as an attenuator. So suddenly the reality we believe is out there and the reality we believe is in there is suddenly quite different. So when you have extraordinary experiences, when you see UFOs, when you have encounters with aliens, again, I've got 5 minutes here and I'll mention this as well. There are people I know that are doing research in London at the moment on dimethyltryptamine. And they're testing encounters with aliens, with entities, with McKenna's machine elves. And one of my associates told me that he was under experimental conditions. He took DMT intravenously and he shot off into what was called a DMT cage. And he's in this place and this entity appears in front of him and it prods him and goes, you shouldn't be doing it this way. This is not the way it should be done. And it backed away into the mists. And he found himself coming to. And he thought, that's really weird. The entity is telling me something that I do want to do. 2 weeks later, he's back in the laboratory, goes in the injection, goes into the DMT zone. The same creature comes over again and says, I told you last time, this is not the way you should be doing it. Now, the question is here, was that entity just a figment of his imagination? Or was it something that had identity and consciousness that was different to his, that he was encountering under these circumstances? And again, this is something I'll be talking about in my other talks over the weekend. So there's a number of things I'll be doing. So in the next few days, I'll be doing a whole thing on time. So I'll be giving all the background information to time that I've been talking about. I'll also be doing a course on alien encounters, which I extrapolated from the one I did here last year. And also on Monday, I'll be doing a 3-hour intensive on the American Californian science fiction writer, Philip K. Dick. Because I argue that Philip K. Dick actually manifested many of the things I discuss here. And I wrote a biography of Philip K. Dick a few years ago. And believe me, there are going to be things I'm going to be presenting in that will blow your mind. As there will be in my one on time. I'll be giving you absolute 100% evidence of precognition that cannot be denied. And the question is, how then do we see the future? So is time filled in with this? So suddenly reality doesn't seem to be what it is. Time doesn't seem to be what it is. Consciousness doesn't seem to be what it is. We are tripping on the end of a huge change in science. We are tripping now on a change in the paradigm of science. And we are lucky enough to be alive to be witnessing these changes. And the things that you have experienced are the things that stimulate people like me to do more research into this. So I thank you for sharing your experiences. And I know a number of you already shared your experiences with me. And I'm keen to know more. Because believe me, you have to listen to people's experiences. Thank you.